Hello viewers, in today's session we are going to discuss some important results related to symmetric and skew symmetric matrices, right? So here we are going to prove these four results where we are given A and B be symmetric matrices of the same order. Then we have to show that A plus B is a symmetric matrix, A minus B is a symmetric matrix, and AB minus BA is a skew symmetric matrix, and AB plus BA is a symmetric matrix, right? So here we are going to prove these four results when we are given two matrices A and B, which are given to be symmetric matrices of the same order. So let us make use of the definition of symmetric matrices and skew symmetric matrices to prove these four results. So here we are given that A and B are symmetric matrices. Now, according to the definition of symmetric matrix, a matrix A is said to be a symmetric matrix if the transpose of the matrix A is equal to the matrix itself, right? And here A is given to be a symmetric matrix, so the transpose of the matrix A, that is denoted by AT, is equal to the matrix itself. And similarly here B is also given to be a symmetric matrix, so therefore we can also write the transpose of matrix B is equal to the matrix B itself, right? So now let us first consider this case. So here we have to show that A plus B is a symmetric matrix, right? So let us find out the uh, transpose of the matrix, that is the sum of matrix A and matrix B. So the transpose of A plus B is given by AT, that is the transpose of matrix A plus the transpose of matrix B, because we know the properties of transpose of a matrix. Suppose we have two matrices, that is P and Q, then the transpose of the sum of the matrix P and Q is given by the transpose of matrix P plus the transpose of matrix Q, right? So using this result we can now write the transpose of A plus B as the sum of the transpose of matrix A and matrix B, right? So now here the matrix A and B are given to be symmetric matrix. So therefore the transpose of matrix A is equal to A, and the transpose of matrix B is equal to B. So substituting here for AT we can now write here A, and for BT we can now write here B. So now we have here proof that the transpose of the matrix A plus B is equal to the matrix A plus B, and which is the definition of a symmetric matrix. So this statement implies that A plus B is a symmetric matrix, right? Because the transpose of A plus B is equal to the matrix, that is the sum of matrix A and B. Now similarly we can prove this result, that is here we have to show that A minus B is a symmetric matrix. So let us find out the transpose of the difference of the matrix A and B, that is A minus B, and here we have T, right? So now again using the properties of transpose, if P and Q are two matrices, then P minus Q, that is the transpose of P minus Q, is given by the transpose of a matrix P minus the transpose of matrix Q, right? So here we can now write using this result, we have AT, that is transpose of A, minus the transpose of matrix B, and again using these two results. So using these two results, we can now write the transpose of matrix A is equal to A, and transpose of matrix B is equal to B. So we have now A minus B, that is the transpose of A minus B is equal to the matrix A minus B. And again, due to the definition of symmetric matrix, a matrix is said to be a symmetric matrix if its transpose is equal to the matrix itself. So this result implies that A minus B is also a symmetric matrix. So now consider the third case. Here we have to show that AB minus BA is a skew symmetric matrix, right? Now a matrix P is said to be a skew symmetric matrix if its transpose is equal to negative of the matrix P, right? So if the transpose of the matrix P is equal to negative of the matrix P, then the matrix P is said to be a skew symmetric matrix, right? So here let us now write the transpose of this matrix, that is AB minus BA. So here again using this result or this result, we can now write here AB transpose minus BA transpose, right? So now here we have the product of two matrices A and B, and here also we have the product of two matrices, that is B and A, right? So here we have to make use of another important result related to transpose of matrices, that is known as the reversal law, right? So if we have, say, P and Q uh, are two matrices, then the product, that is PQ, and here we have the transpose of the product of these two matrices P and Q, then we can now write here the transpose of matrix Q multiplied with the transpose of the matrix P. So here this rule is known as the reversal law for transposes of matrices, right? So here our matrix P is A and matrix Q is B. So using this result, we can now write here B transpose, and then we have the transpose of matrix A, and here also we have to make use of this result. Now in this case B is P and A is Q. So we first write here the transpose of matrix A, and then the transpose of matrix B. So now here we have transpose of matrix B, and using this result we can now write BT is equal to B, and here AT is equal to A, and here we have AT is equal to A, and the transpose of matrix B, that is BT, is equal to B, right? And now here if we take the negative sign common, then we can now write minus, and then we have AB, and then we can now write minus BA. So we have now the transpose of AB minus BA is equal to the negative of AB minus BA, and here if we take P as AB minus BA, then here we see that the transpose of the matrix P is equal to negative of AB minus BA, and AB minus BA is P, right? And this suggests that this matrix P is a skew symmetric matrix, because a matrix is said to be a skew symmetric matrix if its transpose is equal to the negative of the matrix itself, right? So here AB minus BA, the transpose of AB minus BA is equal to negative of the matrix. So this suggests that AB minus BA is skew symmetric matrix. So now consider the fourth case. Here we have to show that AB plus BA is a symmetric matrix. So let us now write the transpose of AB plus BA. So now here we have the transpose of AB plus BA, and again using this result we can now write here the transpose of AB plus the transpose of the matrix, that is BA, right? And again using this reversal law to simplify these two terms, we can now write here B transpose and then A transpose, plus then here we write A transpose. First we'll write A transpose because here the transpose of PQ is equal to the transpose of Q and then the transpose of matrix P, right? So here first we write AT, then we have a BT. Now here the matrix B is a symmetric matrix, so BT is equal to B and AT is equal to A, and here AT is equal to A and BT is equal to B, right? So now BA, we have here BA plus AB, right? And we know that the sum of two matrices is commutative. So we can now first write here AB and then we have BA, because if we have two matrices, say P and Q, then P plus Q is equal to Q plus P, because a matrix addition is commutative, right? So now we see that the transpose of AB plus BA is equal to the matrix itself. And again due to the definition of symmetric matrix, we know that a matrix is said to be a symmetric matrix if its transpose is equal to the matrix itself. So here AB plus BA, if we take AB plus BA as uh, P, then AB plus BA is equal to here the transpose of P, and here we have simply a P. So due to the definition of symmetric matrix, AB plus BA is a symmetric matrix. So now let us prove this important result. So here we are given that A and B are two symmetric matrices. Then the product AB, that is the product of A and B, is symmetric if and only if AB is equal to BA. That is when A and B commute, right? So here we are going to prove that if we are given two matrices A and B which are given to be symmetric matrices, then the product of A and B is a symmetric matrix if and only if A and B commute. That is, the product of A and B is equal to the product of B and A. So we are given that A and B are symmetric matrices. That is, the transpose of matrix A is equal to the matrix A, and the transpose of matrix B is equal to the matrix B, right? And we have to show that AB is symmetric if and only if A and B are commute, right? So now let us here take the transpose of AB, right? So the transpose of the product of A and B is given by the transpose of matrix B multiplied with the transpose of matrix A. So here we have used the reversal law for transposes of matrices. That is, if we have two matrices P and Q, then the transpose of PQ is given by the transpose of Q multiplied with the transpose of P, right? So here the transpose of AB is equal to the transpose of B multiplied with transpose of A using this result. So now here we have the transpose of matrix B, and transpose of matrix B is equal to B. So here we write B, and here the transpose of matrix A is equal to A. So here we write A. So we have now obtained the transpose of AB is equal to BA, that is the product of B and A. And here we are given that if A and B are symmetric matrices, then AB is symmetric if and only if A and B commute. That is, if we have AB is equal to BA, then now here the product BA can be replaced by AB. So here we can now write AB. So when we are given this condition, that is A and B commute, that is the product of A and B is equal to the product of B and A, then BA can be replaced by AB. So here we have now the transpose of AB is equal to the matrix itself. That is, here the transpose of AB is equal to the matrix AB, and due to the definition of symmetric matrix, we know that a matrix is said to be a symmetric matrix if its transpose is equal to the matrix. So this statement implies that AB is a symmetric matrix. So now let us assume that AB is a symmetric matrix, right? So in the first part of the proof, we have shown that if A and B are symmetric matrices, then AB is a symmetric matrix only when A and B commute, right? So in the second part, we'll first assume that AB is a symmetric matrix. So if AB is a symmetric matrix, then AB transpose should be equal to AB, right? So here the transpose of the matrix AB should be equal to the matrix if we assume that AB is a symmetric matrix, right? So now here in the left hand side we'll make use of this result, that is the reversal law, right? So using this result we can now write the transpose of AB as transpose of B, and then we write transpose of A, and here we have in the right hand side AB, right? So now here we are given that A and B are symmetric matrices. So the transpose of matrix B is equal to B. So here we write B, and here we write A. So we have BA is equal to AB, which is this condition, right? That is, here we can now write AB is equal to BA, and which suggests that A and B commute, right? So here we have shown that if A and B are symmetric matrices, then the product AB is a symmetric matrix if and only if A and B commute, right? So in the first part we have shown that if this condition exists, that is A and B commute, then AB is a symmetric matrix. And in the second part we have first assumed that AB is a symmetric matrix, right? And then we have shown that when AB is a symmetric matrix, then A and B commute. That is, the product AB is equal to BA. Now consider this third result. So here we have to show that the matrix, that is the product of three matrices, that is transpose of matrix B, then we have matrix A and matrix B. That is, we have to show that the matrix BT AB is symmetric or skew symmetric according as A is symmetric or skew symmetric, right? So here we'll prove this result by first assuming that A is a symmetric matrix, right? So let us first assume that A is a symmetric matrix, that is AT is equal to A, that is the transpose of matrix A is equal to the matrix A, right? So now here let us now consider this matrix, that is BTAB, and we have to show that this matrix is symmetric if A is symmetric, right? And in the second part we'll show that this matrix is skew symmetric if A is skew symmetric, right? So let us now consider the transpose of this matrix BTAB, right? So now let us consider this product, that is AB is equal to say C. So we can now write here BT and here we have a C. So we are assuming this product, that is AB is equal to some other matrix, that is C. So now here the product, we have the product of two matrices. The first one is BT and the second one is C, which is further the product of two matrices A and B. So now to simplify this expression, we have to make use of this result, that is the reversal law, that is PQT is QT, and here we have the transpose of P, right? So here P is now BT and Q is C. So using this result, we have now first CT transpose of C, then we have the transpose of BT, right? Now here we can again replace this C by AB. So we have AB and here we have the transpose of AB and here we have the transpose of BT. And again, using the properties of transpose, we know that if we have a matrix say X, then the transpose of X is simply equal to X, right? So here the transpose of BT is simply B, using this result, right? So now again applying the reversal law to this term ABT, so we can now write here BT and then we have AT and here we have B, right? So now first we are assuming that A is symmetric matrix, that is AT is equal to A. So let us replace this term AT by A. So we have here BT and here we have A, B, right? So we have proof that the transpose of BTAB is equal to BTAB, and we see that the transpose of this matrix, that is this entire matrix, is equal to the matrix itself. And due to the definition of symmetric matrix, we know that a matrix is said to be a symmetric matrix if its transpose is equal to the matrix itself, right? So here the transpose of this matrix is equal to the matrix itself, provided A is symmetric. That is, the condition is that A is symmetric, that is transpose of A is equal to A. So this statement suggests that the matrix BTAB is symmetric matrix, right? So we have shown that this matrix is symmetric when A is a symmetric matrix. Now let us prove the second part, that is this matrix is a skew symmetric matrix if A is skew symmetric matrix. So now let us assume that A is a skew symmetric matrix, and according to the definition of skew symmetric matrix, the transpose of the matrix A should be equal to negative of the matrix A, right? So now let us consider this matrix. So we have BTAB, and here let us take the transpose of this matrix, and again let us assume this product, that is AB, is equal to C. So now let us write here transpose of B, and AB can be replaced by C, right? And using this reversal law, we can now write here CT, that is transpose of C. Then we have the transpose of that is BT, right? So now here we have again we can replace this C by AB. So we have AB, and here we have the transpose, and using this result, the transpose of BT is simply equal to B. And using again this rule, here we can now write transpose of B, transpose of A, and here we have B, right? Okay, so now we have reached this step, and here we have assumed that A is skew symmetric matrix, that is transpose of A is equal to negative of A. So let us assume this matrix, or this we can replace this matrix by negative of A. So we have here BT, and here we can write minus A, and here we have B. So now we can take this negative sign in front of the transpose of B. So we have minus, and then we have transpose of B and A and B, right? So we have proved that the transpose of BTAB is equal to negative of BTAB, right? So here we have the matrix that is transpose of BAB, and the transpose of this matrix is equal to negative of the matrix, that is this matrix, right? So according to the definition of skew symmetric matrix, a matrix is said to be a skew symmetric matrix if its transpose is equal to the negative of the matrix, right? So here the transpose of this matrix is equal to negative of the matrix. So this statement implies that the matrix BTAB is skew symmetric matrix, provided A is a skew symmetric matrix, because here we have replaced the matrix that is AT by negative of A. So we have proved that this matrix, that is BTAB, is a skew symmetric matrix if A is a skew symmetric matrix.